terms of significance. I know organizing an event is not an easy task. It's very difficult, especially of course international ones like this one. And secondly, many thanks to both Altun and other organizers who invited me here as a speaker. Thanks a lot. And today we are going to start the conference with artificial vehicle and algorithm, honey. And tomorrow, I think the last presentation belongs to me as well. Therefore, today we are going to start with honey, and tomorrow we are going to finish with honey. I hope this conference will be very useful for all of us, like honey. Artificial bee colony is related to optimization area. Optimization, very important area. In our life, we face this process every day, every moment. We optimize everything to get best performance from our life. Therefore, a strategic area optimization. The title is, my presentation is Past, Present, and Future of Artificial Vehicle and Algorithm. The contents presentation include these subtitles. First, I'm going to give basic definitions related to optimization methods, and so on. And after that, swarm intelligence. What's a swarm? Swarm intelligence. We will be going to describe these concepts. After that, honeybees, real honeybees, how they behave, and how they are intelligent, and artificial bee colony algorithm. I introduced this algorithm in 2005 to the literature. And artificial bee colony programming, this is another important variant of artificial bee colony. And last year, I think the first journal article published in an important journal. And of course, finally conclusion. Optimization is finding the best solution in feasible search space bounded by the constraints and parameter ranges. In order to decide whether a solution is better than another, an objective function or this function is used for all design problems. Every design problem means an optimization problem. The aim is finding a parameter vector, minimizing or maximizing the objective function in the defined search space without violating the constraints. Definition. In mathematical terms, for numerical optimization problems, this is the general definition. There is an objective function. Sometimes we try to minimize this objective function. The function is described using optimization parameters or design parameters, sometimes called as design parameters. And there are, of course, lower and upper bounds for the parameters, design parameters. And sometimes there could be some other functions, constraint functions. For example, G, H. This is the inequality constraint function. This is the equality constraint function. Let's have a look at the subgroups of optimization problems in our life. Based on design parameters, for example, these optimization problems can be classified. Continuous optimization problems, combinatorial, integer, binary, etc. And based on objective function, for example, we can classify optimization problems as minimization problem, or maximization problem, or single objective optimization problem, or multi-objective optimization problem. And depending on the existence of constraints, again, there are two subgroups of optimization problems. One, unconstrained or constrained optimization problems. And also, we classify the optimization methods, approaches similarly to optimization problems. For example, traditional methods, analytical methods, and analytical methods, linear programming, derivative-based, structural methods, dynamic programming, branch and column. Most of us, I'm sure, you know some of these approaches, methods. And also, the second main subgroup, modern heuristic methods. Deterministic methods, also is a well-known example of this category. And the heuristic methods, and the single solution-based heuristic method, for example, similarity annealing. It was introduced in 1983 in the literature. And the other subgroup, main subgroup, is population-based, or also this group is called nature-inspired modern heuristic methods, or nature-inspired heuristic methods, population-based methods. And evolutionary algorithms and swarm intelligence algorithms, again, the subgroups of these population-based modern heuristic algorithms or approaches. As evolutionary algorithms, the most popular ones, genetic algorithm. I think we know, most of us know this method. And it was introduced in 1974-75. And differential evolution, evolution strategy, evolution programming, and so on. And swarm intelligence algorithms and column optimization in 1991, 90. And practical swarm optimization, artificial deep learning, and other algorithms. All right, now, nature-inspired optimization. What is swarm? What is swarm intelligence? Optimization at the heart of many natural processes, including natural evolution, social group behavior, and foraging strategies. To tackle complex real-world problems, scientists have been interested in natural processes and creatures as model for years. There has been remarkable growth in the field of nature-inspired search and optimization algorithms, because natural creatures are more successful to solve their problems than us. The two main families of these algorithms are the evolutionary computing methods and the swarm intelligence algorithms. Although both families are generally dedicated towards solving search and optimization problems, they are certainly not equivalent, and each has its own distinguishing features: evolutionary algorithms and swarm intelligence-based algorithms. Two categories. Both research areas are a subfield of artificial intelligence, or more particularly computational intelligence in computer science. Evolutionary computation, the collective name for a range of problem solving techniques based on principles of biological evolution. Biological evolution mainly depends on these two principles: natural selection and genetic inheritance. And genetic inheritance depends on mainly these two operations: crossover and mutation. Most popular parts of evolution algorithms are evolution programming, introduced in 1960. Evolution strategies still use these algorithms, of course, now to solve our problems. And evolution strategies in 1960, genetic algorithms 1975, genetic programming 1992, and differential evolution. Algorithms, and I think it's the newest one at the moment, the most widely used one is differential at the moment, and genetic algorithms and genetic programming. They are used more than these two algorithms at the moment. Now, let's have a look at swarm intelligence, because artificial deep learning is a member of these two algorithms. Swarm behavior swarm behavior is a collective behavior executed by animals of similar size, perhaps being about the same spot or migrating in some direction. Swarming is applied particularly to insects, but can also be applied to any other animal or creature that exhibits swarm behavior. Now, we use this term for all creatures, not for just insects or animals. One of the first definitions belongs to Karaboga. He says swarm intelligence, or this field, is an attempt to design algorithms or distributed problem-solving devices inspired by the collective behavior of social insect colonies and other animal societies. There are several definitions for swarm intelligence and swarm, but one of the first ones belongs to Karaboga. A discipline that, another definition, a discipline that deals with natural and artificial systems composed of many individuals that coordinate using centralized control and self-organization. Two main principles of swarm intelligence are centralized control and self-organization. There are two fundamental concepts which are of utmost importance for the collective performance of a swarm: self-organization and division of labor. Self-organization relies on these four properties of behavior. First one, positive feedback. Positive feedback means good behaviors are followed by other members, individuals of swarm. Negative feedback and bad behaviors are not followed or stopped, or stopping the bad behaviors by the members of swarm. And fluctuations, random behavior. Members of swarm sometimes show random behaviors. And multiple interactions. Multiple interactions means communication among the members of swarm and sharing their information with each other. The second important, of course, properties of swarm intelligence is division of labor. Inside a swarm, there are different tasks which are performed simultaneously by specialized individuals like us. Some of us are mechanical engineers, some of computer engineers, some of civil engineers, and we have to specialize. We have to perform in different or for different tasks to get more success from our job. Inside a swarm, this phenomenon is called division of labor. In intelligent swarms, of course, we saw definitely this property. And swarm intelligence algorithms. So far, I think the most and the first one, the most important that the first one, end-to-end optimization, introduced by Dervis in 1992 or 91. Second one, particle swarm optimization, and the artificial immune system, bacterial optimization algorithm, and of course there are some more in the literature. But these are the popular ones or widely used ones. And the artificial equivalent algorithm, and it was introduced in 2005. Okay, now let's see honeybees. Sometimes we watch a document on the TV and we are surprised how honeybees produce honey and how they find food sources and collect nectar and bring into the hive, and we are surprised. And now how they work and produce honey and communicate with each other. Each hive has about 50,000 bees, about sometimes 8,000, sometimes 70,000, but not more than 200,000. One queen in the hive and 100 female, and about 100 female bees for every male bee. The queen bee lays all the eggs and only leaves the hive once in her life in order to mate. A male drone has only one purpose in life. A male drone has only one purpose in life, to mate the queen. They die immediately after mating. Very interesting. The worker bees are responsible for every job in the hive, except reproduction. Gathering nectar, guarding the hive and honey, caring for the queen and larva, keeping the hive clean, and producing honey, and so on. There are many tasks for worker bees or female bees. Lifespan, queen bee, 2-3 years, male drone bee, 5-6 months, worker bees or female bees, 4-6 months. Very short life, but there are many tasks to do. Yes, now for it, of course here, for artificial bee colony working, the important members of honeybees swarm, forager bees. Forager bee activities. They collect nectar, bees visit 50-100 flowers to collect nectar and pollen on each foraging tree. Collecting police, certain bees only collect police, gathering the resinous substance from trees and carrying it home in their pollen baskets. And 1% of the bees in the hive collect water. Division of labor. We see perfect division of labor. There are some models constructed by scientists, of course, studying on real honeybees. For example, a minimal model of forager behavior of these bees, forager bees, consists of 3 essential components: food sources around the hive, and employed foragers, and unemployed foragers. There are 3 components of the model. And also, this minimal model defines 2 leading modes of the behavior: recruitment to a food source and abandonment of a food source. Food sources. The value of a food source depends on many factors, such as its proximity to the nest, richness or rich concentration of energy, and the ease of extracting this energy. There are several parameters. For simplicity, the profitability of a food source can be represented with a single quantity, such as quality or fitness, especially in the algorithmic phase. We just say fitness or quality of the food source. But profitability depends on several parameters. And we have to consider these parameters to decide whether this food source is good or bad or nice or not nice. Employed foragers. Yes, food sources, employed foragers, unemployed foragers. Now, we talked about food sources, and now employed foragers. They are associated with a particular food source which they are currently exploiting. They carry the information about this particular source, its distance and direction from the nest, and the profitability of the source, and share this information with a certain probability. Certain probability, of course, share this information with a certain probability with the forager bees waiting in the hive. They go outside and find some food sources, and depending on the profitability of food sources or the distance, about distance between the hive and food source, they share this information with the some foragers waiting in the hive. Unpaid foragers. They are looking for a food source to exploit. There are two types of unpaid foragers. Scouts, they search the environment surrounding the nest for new food sources. The mean number of scouts average over conditions is about 10%. Onlookers wait in the nest and finding a food source through the information shared by employed foragers. Now, employed foragers, unemployed foragers. And also, unemployed foragers, it has two subgroups. Scouts, they search the environment randomly to find more rich food sources. The second group, onlookers, they wait in the hive and they watch employed bees, or they take the information given by employed bees to find their food sources. Sharing the information is very important. It's at multiple interactions. Multiple interaction occurs by means of dance, language, communication. Information sharing. Distance information is given, direction, profitability information, and other information about the food sources or the distance about between nest, hive, and food source. To share the information, employed bees or bees use different languages. We call this language dance, and there are different types of dances. For example, vocal dance. Vocal dance, this type dance called vocal dance. This dance, or from this dance, a bee takes information, the distance information, and also direction information. You see this line and this vertical line. The angle is 45 degrees. An onlooker just examines this dance, and she sees this 45 degree, and before going outside, she, of course, turns this direction using this angle between the sun and food source, and follows this direction to find that food source region. And round dance, especially, is performed if the distance is less than 100 meters. If the distance less than 100 meters between the hive and the food source, round dance is performed. Otherwise, vocal dance or triangle dance, just to exchange or change the task, this triangle dance is performed. Self-organization, positive feedback. Okay, now if you remember, we mentioned that there are four properties for the self-organization. The first one, positive feedback. In honeybee or forager bees, as the nectar amount of the food source increases, the number of onlookers visiting it increases too. This behavior, of course, shows a positive feedback for the swarm, forager bees behavior. And as the nectar of a food source increases, the number of bees visiting decreases, and the and at the end, its exploitation process is stopped. Of course, this causes a negative feedback behavior. And fluctuations, the scouts of forager bees carry out a random search process for discovering new food sources. And multiple interactions, bees share their information. For example, employed bees, they share their information about food sources around the nest heap with their nestmates or onlookers waiting in the heap by means of dance language. And you see, for self-organization, honeybees, forager bees, they have 4 main properties. Therefore, they are intelligent. Now, our aim is, of course, in 2005, my aim was to describe a simple and an efficient model for the intelligent foraging behavior of a honeybee swarm. And in that time, I read several articles on honeybees' behavior, honeybees. And after, of course, examining these results, see, and my aim now to introduce a simple model, but efficient model on this behavior. Introducing a new optimization algorithm, of course. First, you have to put a nice model, efficient model, and after that, depending on that model, you have to construct your algorithm, optimization algorithm. Optimization algorithm, as I said, maximization or minimization. The aim of honeybees, forager bees, the aim of forager bees is to maximize the honey in the hive as soon as possible, to maximize. They solve very difficult optimization, maximization problem. Analogy. Of course, you have to first put a good analogy, nice analogy between the real life and the artificial life before, of course, constructing model. Real bees, of course, they work in continuous time. Our artificial bees will work at this time. And memory, they have memory, and they have memory. Real bees try to maximize the honey in the hive, and our artificial bees, they will try to maximize or minimize an objective function related to our problem. And food sources around the hive, in my model, food sources around the hive, possible solutions to the problem, our problem, possible solutions. Number of food sources, population size of solutions. Because every food source, possible food source around the hive, means a possible solutions for our problem. Nectar amount or profitability means fitness of quality of our solution of the problem. Of course, real bees, they work in 2-dimensional search space. Our artificial bees, they will work in n-dimensional space, depending on the problem. Real bees or forager, real bees show independent positive behaviors, and similarly, artificial bees also, they must show, otherwise they cannot become intelligent. And multiple interactions, fluctuations, behavior and phenomenon-based sharing, behavior-based sharing. Now, simple, basic ABC introduced in 2005. It is based on just behavior-based sharing, language, advanced language-based sharing. But we can integrate other sharing mechanisms into the existing ABC, no problem. Because real bees they use different information sharing mechanisms, not only behavior-based sharing. All right, okay, now, very simple. This is the general approach. Very simple. You see, scout this space. For example, take a heap and put somewhere. No, or any bees, foraging bees, don't see around first time they see around, and they are means scout bee space. And after, there is a loop here, from morning to evening. Employee bee space, onlooker bee space, scout bee space. From morning they start until evening time. There is a loop. This is very convenient for the algorithmic structure. Employee bee space, onlooker bee space, scout bee space, until requirements are met. Artificial bee colony algorithm. A full source position, a possible solution to the problem. The diagram is, as we mentioned, of the source, the fitness of the solution. The product of the food source can be defined by using different definitions, no problem, but it's simple. For example, food source I, the fitness of food source I, just divided by all food sources fitness values. This is the probability value of food source I. And onlooker bees choose their food sources or food source region with this probability. Number of sources around the heap, number of solutions in the population. Number of solutions in the population. New food source to be visited, for example, this simple definition can be used to find the neighbor or new food source, to find the new food source. This is, let's say, the existing food source, and this is existing same food source, and this is another food source. Let's say, just take difference and multiply by this coefficient, and after adding this to this difference to this existing solution, you get a neighbor to the food source. Because B, first, she must test the food source nectar amount or quality, and after that, this is not good. Of course, she remembers the previous one. Control parameters. All optimization algorithms have some control parameters. 1, 2, 3, 4. But the important number of control parameters is an important side of the algorithm, optimization algorithm, because we want to use or want to deal with less control parameters. And in the artificial colony algorithm, there are 3 control parameters. Colony size corresponds to the number of food sources. Maximum cycle number, of course, this is iteration number, like iteration number. All algorithms have this control parameter. It's a common control parameter. And this is common control parameter for all population-based or nature-inspired optimization algorithms. And these 2 control parameters are common control parameters. And abandonment criteria, just to decide whether this food source will be abundant or not, we have to use a criteria. This is the limit, this one. And this is algorithm specific control parameter, this one. In this first case, the scouts control the exploration process. and the onlookers and employees carry out the exploitation process. In a good optimization algorithm, definitely there must be a good balance between exploration process and exploitation process. And in artificial vehicle learning, scouts control the exploration process, onlookers and employees carry out the exploitation process. Now let me show some simulation results on basic, simple ABC introduced in 2005. We use some test, of course, test problems, test functions. These test functions are very popular. For example, Riemann function. The aim here is to find the global minimum of this function. Of course, here two-dimensional case. There's two design parameters. There are two design parameters, and this vertical line shows the values of objective function. So, objective function, we try, let's say, to minimize this function, and this design parameters, and there are many local minima, and our aim is to find the global minima, because it means best food source or the richest food source exists in the global minima. Riemann function, for example, Rastling function, Rosenberg function, Average function, Schaeffer function, Rosenberg, yes, sphere function, it's a quadratic function. Number of design parameters, 100, 500, and 1000. For 100, for 500, and 1000 parameters, the results of particle swarm, differential equation, and artificial equal algorithms. You see? There's a big difference, especially for 100,000 parameters. Difference between performance of particle swarm, differential equation, and artificial equal algorithm. And for Rosenberg, again, simulation results, use 100, 500, 1000 parameters. Rastling function, Schaeffer function, Average function. From these simulation results, we can say that, or we can complete some results. Global optimization performance of differential equations depends on the diversity of the initial population. Differential equation is an evolutionary algorithm. In fact, it's not convenient to compare their performance. And but the global optimization performance of differential equation depends on the diversity of the initial population. Differential equation and particle swarm optimization are more convenient for macro problems. Global optimization ability of ABC is better than differential equation and particle swarm. ABC can be used for both numerical and combinatory problems. Tomorrow, the last presentation will be related with the combinatory problem, Sylvan-Seisman problem. ABC. This exercise of ABC has motivated researchers to extend its use to other areas. Now, ABC is used to solve multi-objective optimization, constraint optimization, binary, integer, combinatorial, and several optimization problems, several optimization problems. New versions. Now, there are several new versions, of course, parallel versions, chaotic, hybrid, adaptive versions in the literature. And also, there are several studies which hybridize ABC with other traditional or nature-inspired algorithms. For example, takes ABC, quantum evolution algorithm with ABC combining, and there are several. Application areas. Some of the application areas are given in this slide. Trading neural networks, electrical engineering, industrial engineering, mechanical, data mining, wire, sensor, network image, data research design, civil engineering, architecture. We have already used for architecture problems. And control engineering, protein structure optimization. Use it in everywhere now it's used. A comprehensive survey published last year in Artificial Intelligence Review on artificial recon algorithm. ABC, the work on ABC has focused on algorithmic and application aspects. However, there is still much more to do in this area. Some topics are worth investigating. Self-adaptation of control parameters, for example. Theoretical work, runtime, convergence properties, dynamics of ABC. It's a nice area to work now, especially for PhD students. Modifications to the original structure, traditional and modern heuristic algorithm components, optimization, dynamic and uncertain environments, still open area. Optimization, dynamic and uncertain environments. New label production mechanisms. And if strategies for scout production. Adaptive scout production depending on dynamics of the search. New selection strategies for distributing onlookers sources. Pheromone-based communication. Basically, this is just the dance language based on the communication. Artificial colony algorithm is very simple and flexible, has the ability of taking out a local minimum, and therefore it's able to efficiently search the full search space. Can be applied to solve multi-variable, multi-model, multi-objective, numerical and numerical optimization problems. Can be easily integrated with optimization concepts from different fields. All right, now. Until this point, I just described and presented some basic simulation results on basic ABC. Now, this is the recent variant of ABC. Last year, it was introduced and published in the Information Sciences Journal. Artificial deep learning programming, like genetic programming. Symbolic regression problem. I think most of us know this problem. Symbolic regression problem. We have input data, output data, or we have input variables, output variables, and we have the data for these variables. And our aim is to construct a mathematical relation between these inputs and outputs. This is the regression problem. This is the symbolic regression problem. Traditional linear and non-regression methods fit parameters to an equation of a given form. If there is a model is given, and if we try to find the parameter values of this model, then this is regression problem. And if we don't have the model and the parameter values, then symbolic regression tries to form mathematical equations from mathematical equations by surging the parameters and the form of equations together. Both mathematical equations and the parameters of the equations. If we try to optimize together, then it's called symbolic regression problem. The problem of symbolic regression is an optimization problem, of course, because we try to design something between the inputs and outputs. The purpose is finding the best combination of variables, symbols, and equations to develop an optimal model satisfying a set of fitness cases. GP, genetic programming, in 1992, introduced by COSA. GP is genetic programming. The most popular version of technique for symbol interpretation is genetic programming, developed by COSA. GP can be accepted as an extended version of genetic algorithm. The main difference between genetic algorithm and genetic programming, main difference, representation of the structure, meaning of the representation, GP variants. There are several variants of GP in the literature now. Multi-expression programming, linear programming. ABCP is similarly, ABCP is an adaptation of ABC algorithms to the problem of program induction. Similar to the relation between GP and KA, this adaptation deals with the representation of the problem using more complex structures. In ABCP, full sources positions correspond to computed programs, which are represented by trees. In ABCP, a full source represents a string, a solution in its string form. In this case, full source represents a solution in the tree form, like this one. Do you see? Y is equal to square and ut is yt minus 1 plus 1. Our solution is a tree now. Therefore, full source represents this tree. Computed programs are composed of terminals depending on problem and functions, constants, or different type variables. For this example now, ut, y, t minus 1 and 1, these are terminals, and functions, electrical operations, mathematical functions, programming operations, logical functions, these are functions. The steps of ABC after initialization are creation and evaluation of new functions for employees, selection of functions depending on the